I don't know, look, I think wanting to learn about
It's just love because everyone is graduating. And they're graduating at different weekends, which is good, so I can go to all of them. But also bad, basically on every weekend.
that's what cool. Very nice.
Indian is going to be East
We're also graduating.
Very nice.
Yeah.
So he's gonna have
Is there any special event planned for graduates? I guess not. Senior week.
You're doing 60 or more.
Great. If I can have your attention, please. So first, I just wanted to say thank you to all of you for coming to this event for Fusion Energy Week. As most of you know, this is somewhat the beginning of my career here at MIT and certainly my first Fusion Energy Week. I was very nervous about planning this, so I'm very grateful to see such an enthusiastic audience, both here and those of us on Zoom. So thank you to all of you for coming and making this event wonderful. And thank you to Alex and Maria, who agreed to give us an amazing presentation and who got us that pizza. Or worked for us to get the pizza, fought for the pizza.
You're welcome for the pizza. All right, let's go ahead and get started. So for those who are off-site, I hope you could get pizza for yourselves at home or wherever you're at. Today, Maria and I are going to put on a boxing match of sorts. You know, the race to fusion energy, magnets versus lasers. Right, and you know, kicking off Fusion Energy Week. We had a similar type of presentation about a year ago now at the MIT Energy Conference, and so we've kind of reprised our roles, revamped the slides a bit, and we hope you enjoy. Also, just want to say we recognize a lot of familiar faces here in the audience, so for those folks who know things about magnetic fusion energy, like my part is probably going to be pretty boring for you, and then for those
a lot of my part you will have heard before.
Yeah, this is really sort of an intro to fusion, and hopefully a lot of the folks online will also get a lot out of this. And then maybe we'll hold questions until the very end, but we should have plenty of time to do Q&A and stuff. So.
This will be the third time we battle this out, Alex, I think.
Oh, third time? Okay, nice, yeah. All right. And you've won every time. All right.
Okay, so for those of you who don't know me, maybe some people offline, I'm Maria Gatu Johnson. This is kind of my introduction slide. So I do nuclear diagnostics for inertial confinement fusion and high energy density science, which is why I'll be talking to the laser part throughout this talk. I got my PhD from Uppsala University in Sweden in 2010 in applied nuclear physics. And back then I was actually working on magnetic confinement fusion. So this is the instrument that I built in grad school, the time of flight optimized for rate, or TOFOR neutron spectrometer, look at DD neutrons. And it's illustrated with the inside of the jet tokamak right there. But now, and then I did my postdoc here at MIT from 2010 to 2013, working on this magnetic recoil neutron spectrometer at the National Ignition Facility, which looks like that. That's the actual detector. And I've been working, that's been part of my role ever since. I really analyzed a lot of MRI data. This is a picture from our lab across the street in NW21, where we do all the diagnostic development as a group for the National Ignition Facility in Livermore in California. I'll show you some pictures from there. And for the Omega laser in Rochester in upstate New York, and also for the Z machine, and also starting to do it for some private fusion companies now. So diagnostic development is our focus, and this lab in NW21 is where we did it. So I enjoy showing this picture of our group.
Fighter number one, fighter number two. My name is Alex Tinguely. I'm a research scientist here, also a group leader in energetic particles in magnetic fusion plasmas. I did my PhD here, now started over 10 years ago, and I worked on the Alcator CMOD tokamak, and so for those people who don't know what a tokamak is, we will talk about that. But you can see this picture on the left, the inside of Alcator CMOD, and sort of a picture of me working inside the tokamak, and then me standing outside the tokamak on the bottom. Then I went to JET into the UK for my postdoc for a few years. And so here's a picture of me standing on top of JET, and you can then see inside of JET. And then I came back to MIT, where, as I said, I'm a research scientist. I primarily work on the SPARC tokamak. And again, we'll talk about each of these. Here you can see inside the tokamak hall for SPARC, in the sort of magenta box on the other side of those holes were inside this room here, which is the neutron lab, and I mainly work on neutron diagnostics and fast ions and electrons and fusion plasmas. But why do we do the work that we do? Well, I mean, first, fusion would be a pretty amazing human achievement, but there is sort of a more valuable role that fusion can play in the world today. So when Maria and I were making this presentation now a few years ago, we got this data on the climate change and the world warming. And so here you can see the very sad graph of 50 years of the temperature getting hotter and hotter. And then here's a global map of the temperatures across the world being in white is average, and then all the red is above average, with the darkest red being the record warmest. So back in 2023, you can see a lot of red and a lot of dark red splotches, so that is not good. And I just updated this for 2025. Things do look a little better. There's a little more white, but there's still a lot of red. And so we're looking for a clean energy source that is not carbon producing to help combat climate change. And so here's Bill Gates, who maybe said it best: we need an energy miracle. What could that be? This is the cover of Time, where fusion is unlimited energy for everyone forever. Which sounds pretty cool, right? And then actually the little tagline there: it might actually work this time. So that's also nice. So let's get into what is fusion. What we're doing in fusion is we're taking the atomic nuclei. So in all your atoms, you have in the center a positively charged nucleus. And we're taking that nucleus of two light elements, like these two light hydrogen nuclei here, and we're forcing them together. And if you bring them close enough together with enough energy, they will actually stick together. They'll fuse into a new element and release a lot of energy. So you can see that now these two types of hydrogen come together, helium nucleus flies out, and then also a neutron comes out. And we want to basically harness that energy in fusion. Where does that energy come from? Well, if you actually weigh the different components here, so the two types of hydrogen, which are on the left, the deuterium and tritium, if you weigh those before they react, they are a little bit heavier than the products, the neutron and the helium nucleus. So that really tiny mass difference actually gets changed into energy by Einstein's famous equation, E equals mc squared. And the speed of light is huge, so the c squared is huge, and that's how you get a lot of energy out of this. So the basic idea for what we want to do for fusion on Earth is, number one, heat our fuel enough to turn it into a plasma and have our fusion reactions start occurring. Number two, for this particular type of fusion, those helium particles that are created, we want them to stick around and continue to heat the plasma as well, to keep our plasma hot, to keep the fusion reactions going. And then number three, the neutron that flies out, we want to capture that energy and basically use it to heat up water, turn water into steam that goes through a steam cycle and generates electricity. So in a way, it's very similar to how electricity is currently generated around the world. The parameter that we like to define is Q, and that's the energy out divided by energy in. And so we want that to be much greater than 1. We want to be producing a lot more fusion power than we're using for heating power. And so throughout this talk, we'll touch on the Q values for some of the magnetic fusion, and then also for the laser fusion. So there are three main approaches to confining a fusion plasma, and these are the most studied. There are a lot of companies. We'll actually highlight companies at the end of this talk, and so a lot of different strategies, but these are kind of the three main ones. There's gravitational confinement, magnetic confinement, and inertial confinement. Gravitational confinement has been around for a long time. So basically that's how stars work, right? So all stars are fusion reactors, and so you need something that is the size of the sun in order to have your fusion reactions occur in this energy. Then we have magnetic confinement, which is what I'm going to talk about, and inertial confinement is sort of the laser side, and that's what Maria's going to talk about. The different types of scales that are required for each of these are pretty dramatic. So in the sun, the density, that's N there, is really, really high in the core of the sun. And the temperature is also very hot, 10 million degrees approximately. Now, you need your particles to basically kind of stay around in the same place for long enough to get fusion reactions to occur. And the timescales that we're looking at for the sun are on the order of 10,000 years. But when the sun is billions of years old, you have a lot of time for these fusion reactions to be occurring. For magnetic confinement, on the other hand, we are much lower density, so about 12 orders of magnitude lower. Our temperatures are about 10 times hotter than the center of the sun, which is a huge challenge for fusion here on Earth. And our timescales are much more normal to what humans are used to, so around a second. Inertial confinement, we'll have Maria explain more later. The densities are actually similar to the sun, so they're basically creating little tiny stars, or at least that's how I describe it. I don't know if you would describe it that way. Temperatures are similar, around 100 million degrees. And timescales are really, really, really short. And so I think Maria will talk more about that later. So I am going to focus now on magnetic fusion. And this is the jet tokamak if it was made out of glass, which is kind of a cool picture to see. So what is a tokamak? Basically, we are trying to trap our fusion plasma in a magnetic donut-shaped bottle. So we see our pink plasma donut on the left, and the black line there is our magnetic field line, and our charged particles, those nuclei that want to fuse, they want to follow those magnetic field lines. And in here, they're actually making little tiny spirals around the field lines, and those field lines are wrapping around on themselves. So these particles basically will just move around in a circle forever, and they keep colliding with each other over and over and over until sometimes they'll fuse together. On this video on the right, I want to demonstrate how a magnet can sort of influence a plasma and make the plasma follow those field lines. It's a very different configuration. That is a rare earth magnet that's on the left. It's a dipole magnet, so the field is kind of coming out of the top and going around to the bottom there. And then the plasma is just like basically an arc plasma between two electrodes. So we'll watch this video. As our plasma moves over the magnet, it goes from being basically linear to sort of encompassing the entire magnet, right? The plasma is moving through the magnetic field, and it tries to move from the top of the magnet down to the bottom of the magnet. So that's sort of another type of magnetic confinement. It's not the same geometry, but I think it's a nice demonstration. Also, don't try that at home unless you have high voltage training and all those supplies. So here at MIT, we have a lot of experience with magnetic confinement fusion over many decades, but I just want to highlight one sort of exciting result that we had back in 2016 while I was a graduate student here. So this is, again, the Alcator CMOD tokamak. We're showing a picture of the inside again in the upper right-hand corner. Now, this device was relatively small, about 2 meters in diameter, so 6 feet or so on the inside. The magnetic field strength, this is really what's important to help confine our plasma. We could vary that from 2 to 8 Tesla. And your MRI machine is around 1 to 2 Tesla. So this is significantly stronger than what most humans would ever experience. Now, the Q value, this power out over in, was very, very small in CMOD. And that's just because we weren't using the right type of fuel in the first place. And so it wasn't really one of the main goals of the machine. However, we were able to achieve a new record, which was the highest stored plasma pressure, basically the magnetic pressure fighting against the heat and the pressure inside our plasma. And so on the left, you can see this is the day. A lot of people in the room probably recognize people in the photo. I put a little arrow to where I was standing on that day. It was all very exciting. And here is a video of that discharge. So we're looking inside. You can see the inner wall kind of matching the photo above there. The plasma is very bright. It lasts for only about a second, but that's when we achieved this highest plasma pressure record. Maybe I can play that again for folks. I'll just say that this is not what it really looks like. This is a false color video, and the brightest parts of the plasma are actually the coldest parts of the plasma, where it's emitting visible radiation, which the camera can see. If we had an X-ray camera, video camera, then we would be able to see sort of the shape of the plasma, the real donut shaped. So I was very lucky to have been here for that record and the end of CMOD's lifetime. Then I moved over to the jet tokamak, which at the time was the largest operating tokamak in the world. And I was very fortunate to also be there for their own record for highest fusion energy achieved. So on the right, we're seeing, again, inside the jet tokamak, it's quite a bit bigger than CMOD. So from the center out to the edge, it's about 4 meters. So it's kind of 4 times bigger than the CMOD tokamak. But the magnetic field is smaller, around 3 Tesla. So this machine, one of its sort of general goals was to try to, get close to this Q of 1, but it didn't quite get there. It got to around Q of 0.4, which is not bad, but we're not actually, breaking that break-even barrier. Still, they achieved a nice record of 69 megajoules in terms of a total energy, fusion energy emitted by the plasma. And for reference, 4 megajoules is 1 kilogram of TNT. So it's about 10 kilos of TNT of energy, which is pretty impressive. So let's go ahead and watch this video. Here we're going to see the left half of the tokamak now, sort of mirroring what's on the right. You can see the visible emission down in the bottom of the machine. And as the plasma goes, here's the high power phase where we see a lot of light, and you can see sort of the entire machine lighting up. Again, this is a visible emission, so we're not seeing the X-ray emission from the center of the plasma. Around that same time, MIT was exploring these high temperature superconducting magnets. So high temperature superconductors shown up in the top right corner there. These are very thin tapes, and when you get them cold enough, they can basically carry current forever. So the team here at MIT, in collaboration with a private company, Commonwealth Fusion Systems, built this magnet, which you can see in the picture. It's quite a large magnet, there's some people for reference there. And they wound this out of the high temperature superconducting tape, and they achieved a magnetic field on the coil that was greater than 20 Tesla. So remember, we went from, jet was 3 Tesla, CMOD could go up to 8 Tesla, and now we're getting up to 20 Tesla, over 10 times or even 20 times the MRI magnetic field strength that most people experience. And now this achievement here basically unlocked the funding to pursue building the SPARC tokamak, which is mostly what I work on now. And there's this private company, Commonwealth Fusion Systems, that spun out of MIT. So here's kind of the current status of that device. There's a big site up in Devens, Massachusetts. You can see an aerial view here of the site. In the background is the magnet factory where they're building more of the magnets like you saw on the previous slide. And then in the foreground, this is where the tokamak will live. So this magenta arrows pointing to the tokamak hall. And inside, you can see inside in this upper right-hand plot is where the tokamak will sit. Now, a sort of poster of what the tokamak will look like is up on the far wall there, but it will sit in the center of the floor, and in the bottom right-hand corner is sort of a CAD rendering of what the device will look like with a person for reference. So the magnetic field in the center of the plasma is around 12 Tesla, so 50% higher than CMOD was able to achieve. The diameter is about 5 meters, so it's somewhere in between the size that we built here at MIT and then the size of the jet tokamak in the UK. And the goal is to achieve Q greater than 1, to demonstrate for the first time in magnetic confinement fusion that we can get more power out from fusion than we put in to heat the plasma. Now that picture in the top right is a little out of date. Here is a more recent picture where they've actually just installed the cryostat base, which is where the tokamak will sit, and they're busy building the magnets for this tokamak, and the vacuum vessel is also about to arrive, and we'll hopefully see our first plasma sometime in 2026. Lastly, I just want to touch on some challenges for tokamaks. There are way more than I could put on a slide. It could be a whole other talk. But I would say the trajectory for tokamaks is looking very good, but we have some things we need to address. One is there are inherent plasma instabilities in tokamaks that can lead to disruptions of your plasma and also lead to relativistic electrons. This is something I studied for my PhD. So here's a video, and you're going to see the kind of a normal looking plasma, but runaway electrons are going to hit that metal thing on the right, and you'll see a shower of molten metal at the end of the video. Okay, hopefully you saw that. I'll play it one more time. This is something we definitely want to avoid in future tokamaks because it can melt the metal that we have, and you can see a picture of melting in jet that occurred. Also, there are a lot of materials challenges related to melting. Also, getting power out of the machine. We don't exactly know how that's going to work yet. The sort of plan that was developed at MIT, also being carried forward by CFS, is to use this molten salt flibe, which is shown here in the molten form on the right, and when it's solid form on the left there. So there's a project going on here, Libra, which is going to test how this molten salt is able to breed some of the fuel needed for fusion. This is the plan for the future fusion devices that CFS is going to make as well. So I hope I've given you a pretty good overview of magnetic fusion. Now I'm going to turn it over to Maria to talk about laser fusion.
Okay, so laser fusion works a little bit differently than magnetic confinement fusion, although we obviously have the same goal. Alex showed the fusion reaction at the start, deuterium and tritium given alpha particles, and that's still what we're using in laser fusion as well. But the way that we do it, in inertial confinement fusion, we rely on the inertia of the fuel to keep it together long enough to burn. So this is a very simple illustration of how it works. We'll get back to some examples of how this is actually done. But basically you have a laser or X-rays irradiating the surface of a spherical capsule, heating the surface and increasing the pressure. When you do that, when you irradiate the surface with either the laser directly or with X-rays, as we'll get back to, you get ablation of the surface material. So you have a bunch of material that starts moving off that surface, and then just from momentum and energy conservation, the rest of the material is going to start moving inwards. So you get kinetic energy of the shell that's moving inwards, and that kinetic energy is transformed into heat. So you get heating of the fuel, and you get compression. So you get much higher density and higher temperature. Brings us down here. And once we get hot enough and dense enough, that's when we get the fusion reactions going. And the idea is that the alpha particle is going to stay in this fuel. So once you start getting enough alpha particles generated in the fusion reactions, you're going to get a burn wave going. So you can burn a significant amount of this assembled fuel. And same as Alex said, the neutron will escape. For energy production, the idea is to use the neutron to boil water, essentially, in a reactor. Now we're using the neutron as a diagnostic indicator so we can figure out what's going on in these explosions. We talk about bang time in inertial confinement fusion or ICF, and that's the time of peak nuclear production. So to give you a sense of the time scale, basically this whole the laser pulse, the ablation, the compression, and the convergence all happens over about 10 nanoseconds for a full-scale implosion, and then the actual burn duration is order of 50 picoseconds. So it's really a very, very fast experiment that we're talking about. And just to give you a sense of the scale, the level of compression that you have to do for these, the capsule starts out at about 2 millimeters in diameter. So this is a scale model. But basically the equivalent is if you took a basketball and squeezed it down to the size of a green pea, which also gives you a sense of the challenge involved. Imagine if you take a balloon and try to squeeze it on all sides, that level of squeezing without the balloon bursting out through your fingers. So it's not an easy problem. There are 3 primary approaches to doing this, and 2 of them use lasers. So it's a little bit of a misnomer to call this laser fusion, but we often do anyway because it's simpler for people to understand than inertial confinement fusion. But we have direct drive, which is where the laser beams directly hit the DT-filled capsule. And then, again, just to give you a sense of the scale, it's a 2 millimeter diameter capsule like that. We also have indirect drive, and here, this is what I alluded to on the previous slide, we have a cylindrical cavity, which we call a Hohlraum. It's the German word that basically means cylindrical cavity. And the lasers are incident on the walls of that Hohlraum and converted to X-rays, and it's actually the X-rays that drive the capsule. And I have an example of a Hohlraum here, so I'm going to pass this around and let you guys look at it. This is an actual NIF Hohlraum, but it's from many years ago, so it's not the same scale that's used these days. But if you turn this on its side, you can also see that little fuel pellet in the center of the Hohlraum. So look at it like this first, see the cylindrical can, and then turn it on the side to actually see the fuel capsule. Okay, so that's the indirect drive. We have the cylinder that we use for that. And then finally, we have magnetic drive, which is done at the Z machine. So here we drive a current plasma to get the confinement, and I'll explain it in a little bit more detail on a later slide. So all current ICF facilities are research facilities, not aimed at generating energy. We'll come back to that a little bit later as well. And that in the US, we do have one flagship facility that's pursuing each of these 3 approaches. So let me talk you through those. We have the Omega Laser Facility at the University of Rochester in upstate New York, and this facility is optimized to use a direct drive approach. This is a picture of the full facility, or obviously not a picture, a schematic. And what's actually taking up most of the space here is the laser bay. So this whole part is the laser bay, and we have 60 laser beams at Omega, which ultimately reach the target chamber over here, which is ball-shaped. This is a picture of the target chamber. You can almost not even see the ball because of all these white boxes. And these white boxes are where the lasers enter into the target chamber. So again, there are 60 of them, and they're distributed uniformly around the chamber, optimized for direct drive. You really want to hit all sides of that capsule uniformly with the lasers. This target chamber is 3 meters in diameter, just to give you a sense of scale. And actually, when you look inside, the chamber is not empty. You have a lot of diagnostics entering into the chamber during the experiment to actually be able to figure out what's going on. It's really short time scale, and it's really hot plasmas. So again, Omega has 60 laser beams, and it's capable of delivering 30 kilojoules total to the target, which when we look at the NIF at the next slide, you'll see that 30 kilojoules is a really small amount of energy. So this is really a subscale facility. But experiments at Omega have been really successful over the last few years. And what we can look at, the way we can look at that is, okay, we only have 30 kilojoules of energy available, but if the laser energy was scaled up to 2 megajoules, which is what the NIF can deliver, then will the direct drive implosions ignite? And this is actually from a recent Nature Physics paper, demonstration of a hydrodynamically equivalent burning plasma in direct drive inertial confinement fusion. So we can show the extrapolated fusion yield in megajoule from these Omega implosions. If you scale it from the 30 kilojoules into the 2 megajoules in, you reach the burning plasma regime, but you're not quite in the ignition regime yet. So these are big results from Omega, but they're not quite on the level of indirect drive, even if they were at a full-scale facility. With that, let's take a look at the Z machine. So magnetic drive ICF is being pursued at the Z Pulse Power Facility at Sandia National Labs in New Mexico. And the idea here is that in magnetic drive ICF, an actual current creates a J-B force that's used to implode a gas-filled pre-magnetized target. So we call this maglif, magnetized liner inertial fusion. You start with the pre-magnetization and also a little bit of preheating using a laser. And then you drive the current through to get the J-B force and the compression. And this is done in a machine like this. So the target is about a centimeter tall cylinder, which sits right here, and the current is coming through here. And this discharge can look like this. This is actually a failed discharge. It doesn't normally look like this, but it makes for a pretty picture. The goal of the Z machine is to demonstrate 100 kilojoules DT equivalent fusion yield. The Z machine typically runs with pure deuterium as the fuel, but they've started experimenting with adding some trace tritium. 33 meters in diameter, 26 megaamps current, and 22 megajoules stored energy. And I'm not going to talk more about this today, but just to mention, our group here at MIT is working on, we have one diagnostic installed on the Z machine, which is a compact recoil spectrometer to look at the neutrons from the DD reactions. And we're working on developing a magnetic recoil spectrometer for the Z machine as well. Okay, and then the big one, indirect drive laser fusion experiments are being done at the National Ignition Facility, which I keep referring to as NIF, in Livermore in California. And here you can easily see the comparison to Omega. This is actually the scale comparison. So very similar footprint of the facility, or sorry, very similar layout of the facilities, but the footprint is very different. This is the direct scale comparison. And then the facility again, we have the laser bay taking up most of the space, and people typically talk about that it's the size of 3 football fields, which for me as a Swede doesn't mean a whole lot. And then we have the target chamber over here, which is now 10 meters in diameter, so significantly bigger. And if you look at this, you can kind of see that all the lasers are coming in from the top and bottom instead from uniformly from all sides. That's seen easier in this picture, which is the side view of the target chamber. This blue ball is the target chamber. And obviously the reason for this is that NIF is optimized for indirect drive. So you have that cylinder you're trying to get the laser beams into at the bottom. This is what it can look like. It's obviously just an artist's impression, but you have the cylindrical hole round, laser beams are insulated in rings and converted to X-rays, and then you can drive the capsule. And we already passed around the picture, or the actual model of the hole round. So NIF delivers about 2 megajoules of laser energy to a centimeter scaled hole round. And it's got 192 laser beams compared to Omega 60. Okay, let's see, I don't think we can do sound here, right? It's just, imagine this very eerie, interesting sound, and see if we can play this. This is a NIF beamline movie, just to give you an idea of how it actually works. Okay, and first he calls out shot director ready for shot, and then they show the seed poles. Okay, it's a little jumpy today. So yeah, imagine this really adventure movie kind of music. Okay, we have a seed pulse, which is really small originally. It's pre-amplified. Here comes the seed pulse there. And the master oscillator. And then it's going to get split and amplified in 2 stages, a pre-amplification stage and then a main amplification stage after it's split into all the 192 beams, where it bounces back and forth 4 times until it gets to its final energy. There we're back and forth bouncing. And then eventually we're actually going to get to follow these laser beams into the target chamber and bouncing. It's, yeah, it's more fun with the music, but it's also very irritating. Okay, so now we're moving with the laser beams in from the laser bay into the target bay. This is the wall towards the target bay. Yes. So now you can see the target chamber. And again, it's 192 beams. They're all coming in on their individual beam lines. And you can see frequency from 1053 nanometers to 351, and that's where you had the color change. And this 351 nanometer wavelength laser beams all hit the hole round in the center. And you can see the laser beams hitting the walls of the hole round, and we'll soon get the X-ray conversion. Here are the X-rays. And get the ablation of the surface material. The rest of the material starts moving inwards. And we get burn. Okay, so that's how an experiment at the name works. I think you can look it up on YouTube if you want it with the music too later. Just a couple of fun pictures from the NIF. So this one is from the inauguration. And this one is from one of the Star Trek movies. So this is actually a gamma reaction history diagnostic, which somehow turned into the warp core in the movie. My colleague Hans Hermann at Los Alamos National Lab is the brain behind this diagnostic. And he took his kids to the movies to see this movie. He was very proud to be able to point out his diagnostic. Okay, so you may have all heard, or most of you may have heard, that on December 5th, 2022, fusion ignition energy gain were demonstrated in the laboratory for the first time. And this really was a moment 60 plus years in the making. So what happened on this shot was 3.15 megajoules were output, 2.05 megajoules laser energy input. So that's a target gain of 1.5. And there's a whole gallery of videos about this result if you go to the lasers.ln.gov webpage. And give you a little bit of background to that. So getting to ignition and energy gain took more than a decade of meticulous research at the NIF, and there were many challenges along the way. This is kind of illustrating progress in target gain. So from the first experiments in 2011 with DT and working up towards this result in December 2022, we went from a target gain of 10 to the minus 3, a few 10 to the minus 4, and worked our way through many, many different permutations until we finally achieved target gain on December 4th, 2022. So here are some of the changes, just to give you an idea. I'm not going to go through this in detail. We started with a plastic ablator and tried to do really long laser pulse to drive it to really drive it at like really high compression. And it turns out you have a lot of instabilities you have to worry about when you do that. So basically all these implosions were killed by mix. So the first thing that happened was we figured out how to mitigate some of that high Z mix with a shorter laser pulse, which led to this jump in target gain to 10 to the -2. And then started looking at using different surface material of the capsule from these plastic ablators. We went to high density carbon, which is just another word for diamond, basically switching to mostly diamond ablators starting in 2016. And then figured out ways to increase the coupling efficiency of the lasers using larger capsules, changing the shape of the dimensions of the capsule relative to the whole round, changing how long you let the laser pulse drive the capsule versus just letting it coast at the end, as well as learning how to do cleaner targets. And just to this, I'm going to play a little video. Unfortunately, in Google Slides, it's hiding the text, but this is from a 3D Hydra simulation. And we get temperature on the left-hand side and density on the right-hand side. And below is just saying who did it. It's a simulation by Dan Clark and Lawrence Livermore. And this is just, so this is the capsule-only simulation. And this is one that probably is somewhere in this range. Where you could see, I'm going to play it a couple times, but you could see already at the start movement, both at the top and bottom, and a little divot coming in from the right. So if you see that again, those are actually engineering features on the target. So the way you hold that capsule inside the whole round, a really thin membrane, which we call a tent, it doesn't just levitate, it has to be held in place somehow. And that's what's giving rise to these really bad ruptures at the top and bottom. So learning how to mitigate that by shaping the laser pulse better, using thinner tents was one big thing. The other thing is where the fuel gets inserted into the capsule. That's the fill tube right here. That became a really bad problem too in terms of engineering that would rupture the compression and not allow us to do it uniformly. So we actually went from, I think originally we were working with something like 20 micron fill tubes, and the igniting implosions now have 2 micron fill tubes. So that's thinner than a human hair that's used to inject the fuel into the capsule, which is kind of crazy. So we don't think the implosions look like this anymore, but these were definitely some of the issues that we had to work through to get to where we're at today. Thank you. Okay, so, but once things started taking off, rapid progress was made. So the first thing that happened was in the winter of 2021, where we started having burning plasmas. And this was published in Nature in January 2022. There's a picture of the cover right there. And what that means is really that the alpha particle started doing its job. So this is the article from Nature, Burning Plasma Achieved in Inertial Fusion. And I'm quoting Livermore's Alex Silstra here. Alex was also previously of MIT. He got his PhD from the Plasma Science and Fusion Center, and he was the responsible individual for some of these shots in this campaign. And what he said was, experiments over decades have produced fusion reactions using large amounts of external heating to get the plasma hot. But now, for the first time, we have a system where the fusion itself is providing most of the heating. So really, in this paper, it explicitly says a burning plasma state signifies a transformational change to the energy and power balance in the DT plasma, opening up the potential for rapidly increasing performance. And rapidly increasing performance is what we got. The next thing that happened was in August 2021. This is what we as ICF scientists call ignition. So we got 1.3 megajoules out for 1.9 megajoules in. It's not target gain, but this is the first time we really saw that thermonuclear instability taking off, where it got much hotter, the burn duration got much shorter, and we started seeing that the burning plasma was actually bigger, meaning that it's burning on its way out as it's exploding. So this is what we call ignition. But it didn't meet I think it was the National Academy of Sciences that had said ignition is when the output exceeds the laser energy in. So for a long time, we're not allowed to call this ignition. But for us, this was still really the biggest news. And there were around 470 news reports in August 2021 alone. And Alex Silstra, again, shared the spreadsheet with me so I can show you exactly. Okay, so after this, pretty soon, is where we had this target gain larger than one shot. And this is one of those moments, on a personal note, this is one of those moments in time where you really know what you were doing. So this is me doing a Swedish Christmas concert in between rounds of MRS analysis. So MRS, I think briefly mentioned it on my bio, but that's the detector that we have installed at the NIF that measures the neutron spectra. So this is me and Chris with that spectrometer. And I think I shouldn't take too much time here, but just to give you an idea, the neutrons are produced at the target chamber center. A fraction of them will scatter in a deuterated plastic conversion foil, and forward scattered recoil deuterons will go on to take a different trajectory through this magnet, depending on their energy, to end up in a different physical location on the detector array. So based on where you find deuterons on these plastic detectors, which are processed after the shot in the dedicated etch and scan lab, you can figure out how many neutrons were born here, how hot the plasma was, and how tightly it was compressed. So it's pretty neat. So anyway, I was analyzing that data. I was camping with scouts that weekend. I got the first scans in the morning, found an office at the camp where I could do the analysis, and went and did the Christmas concert and got the next round of scans and was able to confirm the results. So yes, we got target gain, and that was a lot of fun. Since then, we've managed to repeat it 7 more times. So there are now 8 of these target gain larger than one shots on the timeline. And the most recent one was in April 6th, where we got 8.6 megajoules. So you will see that in absolute numbers, this is less than what Alex was getting at the jet. But this is a target gain of 4.1. Okay, so to put this in perspective, it is a research facility, so we're really not anywhere close to putting energy on the grid. There's a lot of losses in the system. We worked our way through. First, we showed scientific break-even in 2014, where we were able to show more energy output, and it was coupled to the fuel. Burning plasma, more energy out that was coupled to the capsule. Then ignition, we actually had more energy out than the X-rays were delivering. And then target gain is when we had more energy out than the laser delivered to the target, and that's where we're at right now. So, but in order for the laser to be able to deliver this much energy to the capsule, the capacitors are using 400 megajoules. So it's definitely not facility gain yet, and that's what people in private companies are starting to work towards now. NIF is never going to reach facility gain. NIF is aiming for ever higher performance with the near-term goal of 10 megajoules, which we said 8.6, so it's really not too far away right now. And they also have an enhanced yield capability, which is pushing up towards 30 or 60 megajoules. It's never going to get to 400 megajoules. So what's needed there are architecture changes, many different things. And the other thing is we need to repeat this often. So there are many steps remaining to make inertial fusion a reality. And this is from a report that I think is about to come out from Measurement Innovations Basic Research Needs Workshop, just to give you a sense. We have shot rate, hertz, on the x-axis, and the performance in terms of gain on the y-axis. And it's just illustrating, so NIF, at the time I made this plot just over a year ago, which was at a gain of slightly over 2, and omega is at a, well less than 1 gain, but can repeat more often at 12 shots per day there. And then we also have a large number of smaller lasers around the US that are actually already capable of operating at rep rate, but don't have any gain at all. They're not intended to do implosions. So where we need to get in order to have an inertial fusion energy plant is up here, where we have a gain of about 100 and a rep rate of about 10 hertz. So there's quite a bit of research remaining to do. One thing though, the NIF is built on 90s architecture, so we think that we could already now get to 10 10% laser efficiency compared to that 400 megajoules to 2 megajoules. That's really bad. That's not what we think we could do these days. And there's been an explosion number of private companies working on this. We'll get back to it right at the end. Okay, yeah, I don't think we really need to talk to this. The plant design will look similar to any other power plant. This is just for the laser driver and the ICF type target chamber, but the rest of this part is the same for magnetic confinement fusion as well. So, Alex, you want to come back up for this last part? Who will win?
We'll see. What's the next slide? That'll probably tell us. No, I mean, we, right.
You want to talk about
Yeah, sure. So, it's clear that both tokamaks and magnetic confinement fusion and sort of lasers in terms of inertial confinement fusion are leading the path, the leading candidates to produce net fusion energy and electricity. I mean, we've seen net fusion energy already with lasers. This is a pretty common plot, which most people have seen before, plotting various metrics. But really what you want to know is you want to be in the upper right-hand corner. And I've highlighted here some of the experiments that Maria and I have worked on, which are already up there. And hopefully, as SPARC comes online, we'll continue to push there. And as these new companies build more facilities, we'll get up into that right-hand corner. Just to briefly say that you saw the sort of pathway for inertial confinement in terms of their idea for a fusion power plant, and Commonwealth Fusion Systems, which spun out of MIT, has taken on sort of the path that was developed here to go this compact high field route. So after SPARC, creating something that is bigger, but similar size to the jet tokamak, hoping to create power that's on the order of hundreds of megawatts of electricity. And do you want to see?
Oh yeah, okay, so the recent results in both magnetic and inertial confinement fusion have generated a lot of excitement and also a jump in private fusion companies. This slide specifically is about the ICF schemes. So there was inertial fusion energy basic research needs workshop that happened shortly after the ignition result. And there's also been a new initiative, which we call IFE STAR, Inertial Fusion Energy Science and Technology Accelerated Research, with 3 different hubs that form a kind of national consortium to push these efforts. MIT is part of the STAR Fire Hub, which is led by Lawrence Livermore. And then, yeah, this is, I think, our final slide. Right?
Yeah. This is just to say that, there are a lot of private companies now. I went to the Fusion Industry Association, which has all of these members, so I just copied everything from their webpage here. There are probably more fusion companies that might not even be on here. I put in these sort of magenta boxes, companies that either MIT is working with or people from MIT have gone on to be founders or work closely in the early startup phases. So it's really exciting to see these companies spin out and of course continue to work with MIT as well, and hopefully at least one of them will succeed. So, okay, the race of fusion energy, who will win? Well, we all win, right? It doesn't matter so much who wins at the end of the day, except, their shareholders when they IPO. But this will be a huge success for humanity. With that, we're happy to take some questions. Thank you for attending, yeah. If I can, I think it would be best to take some questions maybe from folks who are sort of new to fusion. All the other PSFC folks, we can obviously talk to most times. Anybody have a burning question? Yeah, first.
Which instabilities in magnetic confinement are currently kind of subjects of focus? I know about the Cadarash record last year, about 22 minutes, which feels like a long time. Right. What time do we need to get to, and what challenges do we have to get to that point?
Yeah, that's a good question. So I think, you're referring to these really long plasmas like existing for many minutes. And it's true that in the future we'll want to get to creating plasma pulses in magnetic confinement fusion that are on the order of, say, 20 minutes or so. There is some push to do fully steady state, but in magnetic confinement fusion, you have to drive, well, for tokamaks, you have to drive current in your plasma. And so to continuously drive current in the plasma, well, there are different techniques for doing that. If you can pulse your plasma, so keep it on for 20 minutes and let it come back down, which is what they were doing in France and also in China, you know, that might be a little more viable. But there are methods to do continuous current drive. It's some of that's being explored. People here at MIT work out in the D3D tokamak in San Diego, and so and it was also installed on CMOD. So so there are a few ways to do this, and not super long times, but right, 20 minutes still is a long time. And then there are a lot of instabilities. Most of them arise because of the current that we actually have to put in to a tokamak. So there are other types of magnetic fusion devices called stellarators. We didn't even touch here. You're not supplying current to them, and you're creating these really twisted magnetic field coils to create the magnetic geometry that you need to confine all your plasma. And that is a way to have sort of a steady state plasma that could kind of exist for as long as your other, heating or cooling parameters would need. I hope that sort of answered your question.
Yeah, no, it answers it well. I might ask some more detailed questions later.
Sure, yeah, maybe we see, are there any other questions and we can come back to you?
There is one question.
So you're talking about 20 minutes for like an Alcator type of reactor. But yours, I can't even visualize in my head how that would go from this tiny little itty bitty thing into some sort of a mass production where you're actually producing energy. There have to be like billions of those things firing off all the time, right?
That's exactly
Okay.
right. 10 hertz. It's
Okay.
I mean, and there are experiments on
Doing that?
making simpler targets, working on how to inject them. So yeah, those efforts have started.
Guess that would be, it's more like almost like a car engine of like lots of explosions.
So some of the other things actually get easier. You need less tritium than you would for a magnetic confinement facility. It's easier to protect the target chamber, but we definitely have to solve those problems. So yeah, so one of the things that people are working on is wetted foam targets, where you can basically have a foam matrix, a 3D printed foam matrix that you can just soak in liquid DT instead of the ice layers that are used in current targets. So that would be a much cheaper path. And we do have one of our grad students is working on looking at asymmetries in wetted foams, for example.
Question online we could get to, or I guess there are two, but the first one, how can high performance computing and simulations help in ICF and MCF? I mean, it's incredibly helpful, and I think as you are going toward projecting to fusion power plants in the next 5-10 years, they need a lot of simulations to back them up because your investors are wanting to invest a lot of money into these types of things. But on the other side of that, like experiments are really at the end of the day are going to show you if it works or not. So here at MIT, there's a huge push on both sides, and people running in some of the biggest supercomputers in the world.
Yeah, I mean, the NIF is an excellent example of kind of like that back and forth between experiments and simulations. I showed the chart of how the gain has improved over more than a decade. At the outset, the simulation people thought that you were immediately going to ignite, actually dudded the fuel, adding hydrogen into it, because if you had pure DT, it would just ignite and we get too many neutrons that we couldn't count. But of course, it turns out that there are more experimental problems than you think about. Throughout the years, the experiments have backed to simulations, but then you can run a lot more simulations than you can run experiments. So the simulations have also guided what the next experiments would be. And there's a continuous back and forth.
Maybe the last thing I'd just say that machine learning is a huge thing that people are pursuing as well to try to make models more efficient, or some things are often hard to explain as well, and so machine learning can take in a lot of data and try to discover some physics. Other questions? There's another online we can take too, but any in the room here? I'll take this other one online real quick. What recommendations do you have for undergraduates in engineering physics to get into fusion? what would you recommend pursuing a master's or prioritize finding experience after graduation? Yeah, these are great questions. I could take an initial stab. There are a lot of programs for internships and things. I would suggest undergraduates look into, there's a program called SULI, S-U-L-I, which allows you to work at a national lab in the US and kind of get into fusion. And that's a lot of students here, graduate students and myself came through that path. There are also, MIT has open courses. You can start to learn from fusion online. And now I would say in the past, you had to sort of go into grad school to get into fusion, but that's no longer true with all these private companies. I still think, grad school is good. But maybe masters in fusion or even having some experience at a private company can help some people do a few years of work and then come back. So look around at the different companies. They also have internship programs as well.
As do the national labs like Lawrence Livermore, summer internships. Yeah, but I don't have much to add. I think you captured it perfectly.
Any other questions? Yep.
On inertial confinement, what's the primary limitation on rate of fire? So
at the NIF, the primary limit is the architecture of the laser. So you need to have the glass amplifiers cool down. But in the future, it depends on the laser architecture.
So the laser architecture itself, rather than injecting the pellet, or
we have to figure out how to inject the pellet too. But
but that doesn't limit the rate at this point.
Any final questions? I'm sure Maria and I can stick around for a few minutes, but maybe we should call this meeting to a close. So thank you all for coming. Enjoy some extra pizza. Don't fall out.